Okay, so let's find a local linearization for f of x and y is x squared plus y squared at 1, comma 2. Okay, first things first. What is your first guess for f of x and y? So I'm going to write f of x and y is approximately L of x and y, which is, what's your dumbest guess?
F of 1, 2 plus the f.
No, dumbest guess, f of 1, 2, right?
Okay.
Okay, so take 1, 2, plug it in there, what do you get?
5.
5. Okay, so my dumbest idea, right, is that the function x squared plus y squared is always 5 tall. Right, so that would look like, here's a parabola, right, or paraboloid, and I went over 1 and back 2, so I'm like someplace up here, and I said, that thing is always the plane y equals 5. Right? This is dumb. Is it a good approximation locally? Yeah, sure.
Wait.
In fact, actually, you'll note that this intersects in a curve, right? So there's a whole curve, right? This isn't like Calc 1. It's not like I get no points that are right, or just 1 point. Here I get like a whole infinitely many points where this thing works. They're just a curve out of a plane though, right? So I'm not doing that good still.
Isn't that z though, by the way? Plane z? Or
Yeah, what did I say?
plane y.
Oh, that was dumb. I meant plane z. That would be the plane z equals 5, right?
Okay.
Sorry, thank you. All right, what is your next best guess? What are you going to add to this? Yeah, you're going to add the other approximations. So I need here a x slope, and then here an x run, and then I need here a y slope, and here I need a y run. You guys all good with that? It works best if you put this in your head not as a whole object, but just as a like dumbest guess plus x slope, x run, plus y slope, y run. I find that you guys can get it reliably down on paper better if you just have the idea in your head rather than the formula. So what's the x slope? Okay, so I should take the x derivative, right? So I need fx, which is 2x. And then I should evaluate that at x is 1 and y is 2. What do you do with the y information? Chuck it. So I got the x slope is 2. And then what's the x run going to be?
X minus 1.
Yeah, it's going to be the distance you are from 1, right? And what's your y slope? What do you need to go to for a y slope? You need a...
You need f as respect to y.
Yeah, you need the y derivative, right? So you should get
2y.
2y.
2, so we get 4.
So we get 4 here.
Yeah.
But the function was symmetrical. Why aren't those the same?
Because we had a different x and y value.
You guys see that? Like, why aren't those the same? Yeah, because the point's not one of the symmetrical ones, right? The point's kind of offset. So that point has gone further in the y than it did in the x, right? So it's further up the paraboloid, and hence the y slope is a bit steeper. You guys all see that? All right, then what's your y run?
Y minus 2.
Yeah.
Y minus 2. Cool. So there's my linearization. What could I use this for?
An approximation of the function at 1 and 2.
Yeah, we could approximate something. So let's approximate f. What's that? Let me just write. Let's approximate f of 3, comma 2. Yeah, it's probably easier to put it in the original one. That's good. Let's check it against the original one and see how we did. Right? That's why I picked this dumb example, so we can actually check and see how it goes. So f of 3 comma 2 is what?
About
It's about L of 3 comma 2. So L of 3, 2 is 5 plus 2 times something plus 4 times something.
For 2 and 0.
Yeah. So from 1 to 3 was 2x run, right? And from 2 to 2 is 0 y run. So out of this I got 9, right? What was the actual answer?
13.
Yeah. Whoops. You guys see that?
Yep.
So I got 9 plus 4, it's 13. Why is that so far off?
Well,
Good, because it's an approximation and because 2, right? 2 units in the x direction is actually a pretty big chunk of distance when you're talking about from the point 1, 2, right?
They're 50% farther.
You guys see that? Like that's a big increase. And the function's doing some pretty crazy stuff in there. Like at 0, 0, there's a minimum, right? And what I've got here is a plane that goes up in both the x and y directions. If I got on the other side of that minimum, this would be even worse, right? Because the parabola curves back up, but the plane just keeps on going down. What's up, Jordan?
So is this also a more accurate approximation, like lower down in this shape or with a smaller z value, since the slopes are...
Yeah, this will be so the radius on which the approximation is good will be bigger lower down. Yeah, that's a fair point. You guys see that? Like when this thing gets steep, right? Your linearization gets steep too, but the rate of pickup is going to be pretty high up there. So this approximation is going to be pretty good locally, but locally might get smaller depending on where you are on the function. You guys all see that? Okay. This is probably a good technique to know, right? But really, this is maybe for far runs, right? Not a great technique to use. This is a good technique on a micro scale. If you want a bigger radius, you need to add some more information to this. And that gets really, really complicated in Calc 3, so we just give you other techniques later.
Does it tell you if it's differentiable at a point though?
Yeah, this does tell us, because we were able to conjure this thing, that the function x squared plus y squared is in fact differentiable at the point 1, 2.
But
You guys see that? But I knew that in some sense because I differentiated it in both directions at that point. You guys see that? Like the thing I needed to build this was I needed to be able to evaluate the function and I needed to be able to calculate an x slope and a y slope.
but it only tells you that it is differentiable. It doesn't tell you what the derivative is.
Oh, yeah, in some sense, this is the derivative information.
Okay.
You guys see that? Like, in some sense, in Calc 1, we were after tangent lines. And so the derivative and the tangent line information were the same thing. Here we had those partials, right? Yeah, in some ways, this contains all that partial information.
Did you get the partial? Like, could you use this for the partial derivative?
Yeah, we could definitely use this for finding the partial derivatives. If somebody gave us a tangent plane, right, we could pull the partials off of it. You guys see the equation of this tangent plane, right? Maybe let me pull the equation of the tangent plane out.
So with the partial derivative.
So this tangent plane's equation would be what? Z equals 5 plus 2x minus 2 plus 4y minus 8.
which ends up being -5 plus 2x plus 4y.
Okay.
Once you get all
So I got -5 plus 2x plus 4y is z, right? The standard form of a plane includes what? We did this, guys. No, Wednesday. What's the standard form of a plane? You guys remember? It's like the standard form of the line. That's the one you never use, right?
AX plus
AX
BY
plus B.
plus
AX plus BY plus C equals 0, right? Or equals number, rather. So that would be -2x minus 4y plus z equals -5. You guys with me on this? Okay. What's the normal vector? -2, -4, 1. Okay. If someone gave you a tangent plane, you could pull the normal vector off of it, right? Even if it wasn't written this way. You could read the normal vector off. And then you could make the normal vector by multiplying by a scalar have a z coefficient of 1. You guys all see that? And then these two would be the minus,
Minus I minus J.
Oh yeah, that was 2.
no, even better. This is minus fx, and this is minus fy. Okay, see that? So if somebody gives me a tangent plane, we can kind of relate that information and this information to get those derivatives out of there. Alternatively, we could solve for z and then write it like this to find the x slope and the y slope.
So
You guys see that? It's the same process. So if someone told me that my tangent plane was 4z is 3x, 4z minus 3x plus 4y equals 17, right? What's your normal vector?
you want to force the Z to be 1.
Yeah, so I'd say my normal vector is -3, 4, 4, right? And then I want to make it look like this.
So divide by 4.
So I can do n over 4, right? Is -3/4, 1, 1. And this guy's minus fx, and this guy's minus fy. So now I could know that my fx at whatever point I'm talking about is 3/4, and my fy at whatever point I'm talking about is -1. Kind of with me on that, Sevens? What's up, Ray?
So regardless of whether it's a positive or negative value in the reticence in normal, then it's still going to be negative fx and negative fy?
Yeah, and that's purely because to get that normal vector, I had to push them to the other side of the equation, right? Yeah, we'll have occasion to use this trick actually later, which is the only reason I'm showing it to you. Cool. Another thing we could do is we could conjure the equation for this plane out of that information, which is a little bit weird. But that's actually, like, I didn't justify this equation for this plane. I just kind of, right? You guys all recognize that you were slightly lied to earlier? And no, maybe. Okay. So those are the slight lies I was talking about. Like, I didn't really justify this. I just kind of waved my hands and brought it up. If we wanted to get a firm justification for this, we'd actually do it the other way. We'd come up with a couple of vectors and cross them and get this equation. That's cool?